Excellent. Okay, so hello. My name is Scott Scott Grizzard from the University of South Florida. This is Calculus Fall 2020. Today is Lecture 5A, Class 5A. We're going to be using the power rule and some other derivative rules. I'm hitting my head on the thing. Ouch. So that's what we're doing today. I was going to prove the power rule today, but given that there were some algebra things that you guys seem to be understanding some things, like the drawings very, very well, but some of the algebra is a little was an issue. I'm going to go back, and that's because of the online thing, and I didn't think of that, which is on me. So what I'm going to do today is I'm going to go over the basic, the power rule. I'm going to do a bunch of derivatives of basic functions, and then we'll go over some of the stuff that you'll see on WebAssign if you're in my class. So how to mix and match these kind of basic rules. And the plan is for us to state the power rule tonight, and then we'll do the proof for it on Thursday. I think I mentioned this in class. If you were in class today in the group sessions, you already heard me say this. Yes, so that's where we are. Awesome job, by the way, on the test, guys. If you didn't get the grade you wanted, please remember that we are dropping the lowest test score can be replaced by your final if your final is higher than your lowest test score. So if that was this test, that's okay. If you're missing algebra and things like that, please come see me. Let's fix it. There's nothing wrong with not understanding something coming out of, public school, that is today, but there is something wrong with being too embarrassed to get it fixed. So don't feel embarrassed if you have problems with your algebra and things like that. Please just come see me. Let's talk about it. And let's get it fixed. So enough about that. But we will be talking about the algebra today a little bit more. Just to make sure everyone's on the same thing. Also, you'll notice that I'm trying to speak more quickly. And I'm going to waste time about the reason I'm speaking more quickly, but the reason is because people were saying I just do stuff up. Okay, so let's talk about what we're going to talk about today. Thank you for the person who is telling me that my green screen's not up. Yes, I'm actually looking at it this time to make sure I don't do that. Thank you very much. I did do that last time. Okay, so what are we going to talk about today? So again, last time we did the sum, the constant multiple, and the constant rules, and we proved the power rule for positive integers. I should say we didn't prove the power rule in full general. We just did it for positive integers. For exponents that are positive integers. Tonight, what we're going to be talking about is using that. And again, we actually have the power rule for more than just positive integers. But to start with, let's talk about exponents again. And we're going to go over a whole bunch of other rules that are in your book in section 2.3, some of which, like the sign rule, we've actually already proved. But let's just take it aside for a moment and talk about exponential notation. So let me ask you this. When you see the number 8, right? What is the number 8? Okay. What is the number 8? What do we think about when we think about the number 8? Okay. Well, if you're a logician, you think of, it's the number 0, 1, 2, 3. It's the set containing 0, 1, 2, 3, 4, 5, 6, 7. You could think of it as an integer. You could think of it as 0 plus 8, or the thing's 8 away from the origin. But when most mathematicians hear the number 8, a thing in their brain goes off. All right, and this is because we've been dealing with numbers so long and stuff like that. And this is one of the reasons why we are mathematicians, right? We actually like these things. But when you say the number 8, a mathematician immediately thinks too cute. That's what number 8 is to a mathematician. And to anyone who's been doing this long enough. Okay, so 8 to a mathematician 8 is 2 cubed. It's 3 2's, right? It's 2 times 2 times 2. That's what we think of, right? That's kind of the number on its birth certificate, right? Prime factorizations are unique and in the integers, and that's how we think of it, is 2 cubed. And likewise, the number 4 is that, and such. So what is the cube root of 8? So the cube root of 8 oops. Let's do that again. The cube root of 8 is not just 2. To a mathematician, they see this, 2 times 2 times 2. Okay? So what is the cube root of 8? Well, the cube root of 8 is 1/3 of the 2-ness. Right? That's what we think of when we think of the cube root of 8. 8 is 2 times 2 times 2. And now I want 1/3 of the 2-ness of 8. How do we feel about that, 1 to 5? This idea that numbers have prime factorizations, and what I want is 1/3 of that. Likewise, 9 equals 3 times 3. So when I talk about the square root of 9, the square root of 9, I'm actually talking about half the 3-ness. Okay? So if I'm going to think about it that way, and if you think about it, this makes sense, right? If I have 2 cubed is 3 2's. Right? So 2 cubed equals 2 times 2 times 2. Well, if what I want is 1/3 of the 2-ness of 8, in other words, 8, right? Just like here, I had 2 cubed. Now what I'm going to do is I'm going to take 2 times 2 times 2, and I'm going to take 1/3 of the 2's. Okay? So instead of 2 times 2 times 2, I'm going to take 1/3 of the 2-ness. And that is 8. Okay, so what about 8? What about the square root of, what about the cube root of 8 squared? So new problem. What about this one? I want 8 squared and I want the cube root of it. Now I could square 8, I'd get 64 and then take its cubed root. Right? I could think of it that way. And then how do I do that again on my calculator, by the way? It's this X button here, somewhere on here. There's a cube root button, but it's got like an X in it. Right? Or I could think about what this is. If instead of 8 squared and then the cube root of it, I think instead I want to double the number of 8s and then take 1/3 of the whatever it is, right? So if I'm doubling the number of 8s, if I take 2, so if I think of it this way, the cube root of 8 squared. Well, that's really the cube root of 8 times 8, which is really the cube root of 2 cubed squared. But if I line these up, I'm going to have 6 of these 8s, right? I mean, I have 6 of these 2s. So if I think of the cube root of 6 2s, and then I want 1/3 of the 2-ness, I wind up with 2 times 2. Or I could think of it like this. 8, the cube root of 8 squared equals 2 times 2 times 2, and I want 2/3 of the 2-ness. So I take 2/3 of the 2. How do we feel about that 1 to 5? I'm just taking 2/3 of the 2-ness, of the multiplicative 2-ness. Okay. Well, I thought that was the coolest thing I ever saw when I first saw it. I mean, 2/3 of the 2-ness? That's kind of neat. All right. Then again, I'm teaching math. Okay. But that's why we have integer notation. So, the nth root of x to the k equals x to the k over n, which is the same thing, and I'll put a little like thing where defined. Right, because sometimes I wind up in complex number land if I take the square root of negative numbers. So for any x greater than 0, but, slight caveat there, but don't worry about it. Which is the same thing as the nth root of x to the k. Again, caveat for negative numbers. All right. It's not really the same because, if I can't take square roots of negative numbers, but, I can't take even powered roots of negative numbers. And this is the notation. So for the example for the power rule, okay, the derivative d over dx of the cube root of x is going to equal the derivative. I've done nothing but algebra. This is all just algebra. No calculus has been done here. the derivative of the cube root of x equals the derivative of x to the 1/3. Okay? Now, recall the power rule. Okay? If c is a real constant, and f of x equals x to the c, then as long as x to the c, x to the c minus 1 is defined, and there are places where it's not, d over dx of x to the c equals cx to the c minus 1. And this is the big rule that you need to remember. You know, looks a bit like a Christmas tree. Okay? That's the thing you need to remember, because if it's not defined, it's, yeah, well, obviously it's not defined. Right? I can't take the cube root. If x is 0 and c is 1/3, you're going to wind up with an infinite derivative, which of course is not a derivative at all. Okay, so let's go back to this thing here. I've got d over dx, x to the 1/3. That's going to equal, by the power rule, 1/3 x to the 1/3 minus 1. And that equals, of course, 1/3 x to the -2/3. Which brings up the question, what do I mean by a negative exponent? Okay. Now, okay. Well, recall the following rule. X to the a times x to the b equals x to the a plus b. And if we think about this, it makes sense, right? Example. Right? What's the example? So let's say 1,000 times 100, which equals x cubed times x squared. Well, when I multiply these together, how many zeros are going to be left? I'm sorry, not x, 10. 10 cubed times 10 squared, right? Now, when I multiply these two numbers together, I'm going to wind up with 1, 2, 3, 4, 5 zeros. That got to be 10 to the 5th. How do we feel about this rule, 1 to 5? And are there any questions? If you have questions, please ask. Okay. Excuse me, I'm sorry. I need to see the other thing here. Okay. All right. So this is, this rule better be there. Now, well, what is 1,000 divided by 100? Well, that's going to equal 10, right? I take the zeros and I chop them off. Okay. So a negative exponent is division. And if you think about it, that makes sense, right? Because 1/2, okay, if I have 2 to the 4th, right? If I have 2 to the 4th and I multiply it by 1/2, it should be it should be the same as 2 to the 4th over 2. So 1/2 should be 2 to the negative 1. How do we feel about that 1 to 5? This is a little bit of an idea here, right? There's supposed to be there it is. Okay. Reminder, there's public stream that way. Nope. There's public stream on one side of this thing, and then there's public chat on one side and private Discord chat and Discord class chat. According to the statistics, there's 14 people here, and no one's giving me 1 to 5s. One person is in Discord, which is awesome. Okay, anyway. This makes a little sense, right? 1/2 should be 2 to the negative 1. So, that's what I mean by 1/3 to the x to the negative third. So to go back to our thing, x to the negative 2/3. So 1/3 x to the negative 2/3. What was it? Was it 1/3? Yes, 1/3 x to the negative 2/3 equals 1 over 3 x to the 2 over 3, right? So when I move it to the bottom, I put a positive exponent on it because it's division now. It went from a negative exponent on top to a positive exponent here. And then that is 1 over 3 x squared. Should actually be the cube root squared. 1 over 3 x, nope, this is right, x squared cube rooted. Okay. So how do we feel about that? 1 to 5. If it's a negative exponent on the top, is a positive exponent on the bottom, and vice versa. If I have a negative exponent on the bottom, I move it up to a positive exponent on top. So let's do a to the negative k over 1. All right, so I just flip them around. Okay, so let's deal with some of these problems. By the way, don't simplify in this class unless you're told to. Okay, so don't do this. Let's do an example, and then we'll put up some rules for these. So, let's do d over dx of 1 over the cube root of x to the 5th. Okay, that's 1 over the cube root of x to the 5th. Okay, these are the steps to dealing with these weird things. First, convert everything to exponential notation. Radicals first, then fractions. Okay, so I've got this thing here. What am I going to do to it? So this is the derivative. Now notice, when I do this, I'm going to keep the derivative inside. I'm not going to mess with this derivative sign. This right here means take the derivative of. Oops. And it does that again. Okay. All right. So I'm going to take the derivative up. That's d over dx, not to be confused with dy over dx. Okay? All right. So this right here, you can think of it as a verb. It's a command. Do this. I'm going to convert everything to exponents first. Radicals first, and then the fractions. So this is the derivative. Notice I still have the derivative sign here because I haven't evaluated a derivative yet. I still need to evaluate the derivative of what's inside. Okay, this x to the 5th cube root. This is going to become x to the 5/3 on the bottom. Okay. That equals the derivative. I have not taken a derivative yet, or I should say, I still need to take the derivative of what's inside. X to the negative 5/3. To multiply anything needed. In this case, nothing. And then 3, apply the power rule. Okay. So there is no 2 here. So now what I'm going to do is apply the power rule. And no, you don't need to write that every time for the power rule. The power rule is one of those which, duh, you're using the power rule. We got it. Okay? All right. So now what we're going to do is we're going to do negative 5/3 x to the negative 5/3 minus 1. Right? Because that's the power word. I take what's up top here, pull it down, and then I subtract 1. And that is going to be negative 5/3 x to the negative 5/3 minus 3 over 3, which equals negative 5 over 3x to the negative 8 over 3. 4. Simplify nothing but the exponent. What I mean by that is do nothing but do the subtraction. Do nothing but subtract negative 1. And I personally think you should be able to leave it, but people have gotten marked off in the past for that. Okay? The only simplification I'm going to do is this. Do not convert it back. Unless it says prove something is equal to something else, do not convert it back. Okay, this is the answer you want. That is your final answer. The only simplification you need to do is subtract the 1 from the exponent by taking, if you have to do something like that where it's a fraction. The whole room is shaking here. Earthquake in Florida? No, I just hit my knee on the desk. All right, so 1 to 5, how do we feel about that? Little 1 to 5. Tell me how you feel. Tell me what you think. Okay. Let's do another example. All right. Let's say the problem reads this following. Okay, so the example reads like this. Let y equal the square root of x over the fifth root of x. We'll do the square root of x cubed over the fifth root of x. Okay. Let me put exponent rules here. So I need to apply exponent algebra is what I mean by that. Multiply anything needed. Add up my exponents, subtract up my exponents, and stuff like that. Okay. Oh, you want me to go the other direction? Okay. All right, so here's the other example. So, and then I want to compute dy dx. Now, this is important. This is notational. This is a noun. Okay? That's important to remember. dy over dx is the output of the derivative. Okay? It's not a verb. Here's how you do this. dy over dx, this is Leibniz notation, equals. Now, I'm going to put the operator in the front, but notice there is no y on the top. Okay? If I put the y on the top, it's a noun. But if I say d over dx, that means take the derivative of. So, dy over dx equals d over dy of y. You can think of it as a fraction in the terms that I put y in front. It's not exactly that, but you can think of it that way. That's how Leibniz thought of it. That's good. Leibniz was really, really smart, and how he thought about it was good enough for me as far as I'm concerned. We don't need any of that limit garbage. We can just go with infinitesimals, and I'm on board with that. That's just my personal opinion, right? People later proved that what he was talking about was the right way to think about it, and the French got all French about it again. But they're French. Now, I'm going to put in y here. The derivative with respect to y, the derivative of y with respect to x is the derivative with respect to x of y. And it's not multiplication, but I can think of it a little bit like that. Equals, well, d over dx, this is y here. So the derivative of x cubed, of the square root of x cubed over x to the fifth. Okay? Now, what I'm going to do, I haven't done any calculus yet. No calculus has been done so far. I'm going to do algebra only. I'm actually going to put this on the next line. This is only algebra. D over dx. No derivatives have been evaluated. X, the square root, remember there's a little 2 in here implicitly. The square root of x cubed is x to the 3 over 2. And this right here is x to the 1/5. Now, again, algebra only, no calculus done. By the way, you don't need to write algebra above your equal signs. I'm doing that to communicate. I'm not doing any calculus. D over dx. Now, I'm going to do x to the 3/2 times x to the negative 1 over 5. No calculus has been done. Algebra again. D over dx, again, I still haven't evaluated that derivative. Okay, now I'm going to have to do a little math here, common denominator stuff. 3/2 minus 1 over 5 equals algebra again. Let's see, the common denominator is 10. X to the 15 over 10 minus, the minus goes up there, minus 2/10 equals x to the, x to the 13 over 10. Nope. Doesn't equal that. It equals the derivative of x to the 13 over 10. Still no calculus. 1 to 5. How do we feel about that? No calculus has been done. Okay? No calculus done. This is all algebra. Now I apply the power rule. And no, you don't need to write it up there, but I'm going to do it for a while in order to communicate. Now I'm going to evaluate that derivative. Now I'm going to evaluate the derivative. Just like evaluating the limits, now I get rid of the sign. So equals the derivative of this is 13 over 10 x to the 13 over 10 minus 1. If you are dealing with fractional exponents or negative exponents, please, oh please, do the -1 step. Right? So if I'm dealing with x squared, I'm going to say 2x to the first without doing an intermediate step. This is my personally. You won't get marked off for it unless you make a mistake. And I make mistakes all the time with these things, right? I'm not going to try to subtract 13 over 10 minus 1 in my head, even though it's going to wind up being 3/10. I'm not going to try not to do that. I'm going to, if I'm dealing with something positive, if I'm dealing with something in a fraction, or if I'm dealing with a negative, I'm going to write it out. Okay? If I'm dealing with that, I'm always going to write it up. That's my personal preference. I don't care if it's x to the negative 1. I don't remember when I take the power rule that it should become x to the negative 2. I write it out. Now, notice the derivative sign is gone. Now I'm going to go through it. It's 13 over 10x. And be careful with this x. It's not on the bottom, it's on the top. X to the 13 over 10. I would probably skip this particular step because it's 10 over 10. This step I might skip. Writing the common denominator because it's kind of obvious what it's about to become. Okay? 3/10. And then stop here. How do we feel about that problem, 1 to 5? Okay. All right. So that's the power rule. Okay. Now, if I'm applying to some polynomials, here's what I'll do for something like, so here's a problem for you. Problem. Let y equal x to the cubed times the fifth root of x squared plus 7 plus 10. Find dy over dx. So now I'm going to combine a bunch of rules that I had last time. Okay? Now, tomorrow or next time we're going to get the power rule. I'm actually going to state it tonight. When we have the power rule, our temptation is the product rule. When I have the product rule, I'm going to be tempted to do that. But this problem here is actually easier to just apply the power rule. Okay? Just do some algebra first and apply the power rule. And a lot of times that's an easier problem. Or, apply the power rule a few times. Okay? So, solution. Okay? dy over dx equals noun, the derivative, verb, take the derivative of. I mean, it's not really, yes, but it's easier. It's easiest to keep them straight if you think this is a noun and that's a verb. They're not really that, but yes. Yes, so the person in Twitch chat has said exactly what we're going to do. We're going to distribute x cubed and rewrite the radicals in exponential form. And that's exactly what we're going to do. But I'm going to write it out. X cubed times the quantity, the fifth root of x squared plus 7. I'm going to convert first. And don't forget the 10. I'm going to convert first. So I'm going to do d over dx, x cubed times the quantity, x to the 2 over 5 plus 7 plus 10 equals, still algebra, d over dx, x cubed, x to the 2 over 5 plus 7 x cubed plus 10 equals d over dx, x 3 plus 2 fifths, 3 plus 2 over 5 Let's see. This common denominator is going to be the 15th, isn't it? 3. No, it's going to be 5, obviously. So this is going to be 15 over 3 plus 2 over 5. I know I kind of just did that. Plus 7 x cubed plus 10. Still doing all algebra. Equals d over dx. X to the 17 over 5 plus 7x cubed plus 10. Did I do all my algebra correctly? 3, that should be x cubed. Yes, 7 still there, 10 still there. 15 over 3 is 5. That should be a 5, not a 3. I don't know why I was thinking 3 at the time. That doesn't look very good. Trust me, it's a 5 there. 17 over 5, that's right. Perfect. Now I'm going to do the calculus. Now, I could do sum rule, okay? So this I would actually skip. I would skip this step because everything in here is a sum, but I'll write it out for the moment. Yeah, so I'll just write this out here for the moment. Now, I'm definitely not going to write the other. I'm not going to do the constant multiple. I'm going to do the constant multiple rule, but I'm not going to write it out. I would skip this step for a polynomial, by the way. Right? If I'm dealing with sums and constants and constant multiples, I would skip those just because you don't really need them. I would never skip a product rule step, and I would never, ever, 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 ever skip a chain. But I might do some I'll skip. But I would write them out for yourself at first. Now I'm going to do some calculus here, some more calculus. Now I'm going to apply the power rule and others like constant multiple rule. Like constant multiple rule, I'll put that in here. CMR. And then CR, because I'm going to apply the constant rule there. I'm just going to do a bunch of stuff at once because this is now simplified. Now I'm going to do 17 over 5x. So again, normally I would skip this step. I'd do all of these at once. 17 over 5x to the 17 over 5 minus 1. I would not skip that step. I might do to the 5 over 5 just for my own, I might do that, but I would not skip the step entirely. Plus, and then this is going to become 21. I would skip this if it's just a whole number. If it's a fraction, if it's something complicated, I would actually write that out. X squared. This is a positive exponent. That's an integer. A positive integer exponent, I skip the step on the minus 1 bit. Plus, the derivative of this right here is 0. I write the 0. Okay, it tells you what happened. I want to do that because if I mess something else here and I don't write that 0, it's going to look like this 10 went nowhere. Or this 10 is part of this part. I want to explicitly say what happened to the 10. Okay. All right. Now, the only simplification I'm going to do is I'm going to do 17 minus 5. One to 5, how do we feel about that problem? Combining a bunch of rules. Okay. Again, it was algebra, 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 algebra. right? Because the derivative of a constant function is 0. If I take the line 10 and I take its derivative, there's no change, right? Y is always the same. You could think of it as 10x to the 0, but then what about the x to the negative 1 bit? I mean, if that helps you think about that, then go for it. All right. If you think of 10x to the, if you think of constants as 10x to the 0, apply the power rule, you go. Okay. I'm okay with you thinking that. Just don't then confuse yourself. Well, what about the x to the negative 1? I mean, what if it's not defined? It doesn't matter. The derivative of a constant is 0. So you can think of it in terms of the power rule, but then don't confuse yourself about, well, can I apply it here? Because we're negative. Which is fine. I'm not, opposed to thinking that. Can we apply it here? Because it's 0, right? What is the derivative of 0? 0 x to the 0, and what happens to the x? What if the x is negative? It doesn't matter. So you can think of it in terms of the power rule, but I would be careful. It's just much easier to think of the derivative as constants as 0. Okay. So let's look at some other derivatives, okay? Right now we have d over dx of, oops, this pen is very black and very large. Right now we have d over dx, let's throw some rules together. We have d over dx of x to the c equals cx to the c minus 1. This is the power rule. Now, notice something. The exponent is fixed. The base moves. That's important. I'm nudging the exponent. I'm nudging the base, not the exponent. Okay? For constant c, by the way, d over dx fc equals 0. And just remember in the back of your head that what I'm doing is taking the derivative of a constant as a function, right? So this is really f prime of x equals 0 if f of x equals c. If my rule is that the y value is always c for whatever x domain I have, that's the thing. And again, don't confuse yourself. Just keep it back there in the back of your head. I'm really talking about something that's happening as a function. But don't confuse yourself on it. I say as I confuse you. Let me confuse you on it, not yourself. All right, now, here's one that we're going to do. The book does it later, but I'm going to do it now. C to the x. So c is constant and x moves. This is the exponent rule. Okay? And that is c to the x log c. This is very important. There's a very big distinction between these two functions, right? There's c to the x and there's x to the c, and they're very different functions. Okay? where C is constant. Okay, that is extremely important. Okay. Now, there are a bunch of different ways to, you have to do logarithmic differentiation, and we're going to get into that. But there is a different method for getting x to the c. You cannot use the power rule on those. All right. And we will get into that. All right. The next one, the derivative here, d over dx of sine of x equals cosine of x. D over dx of cosine of x equals negative sine of x. We proved this in problem set 3, Chaser. It was that bonus packet. You need the, that's why you have to do a special limit of that's why you have to prove the special limit sine x over x as x goes to 0 equals 1. And you can't use L'Hopital's rule because you actually need that limit in order to prove this derivative. And while you're at it, you also get that cosine and sine are both and the proof of this is similar, proof in your book if you care. I'm not going to ask you to prove those on the test, but it's good to know that there's a reason you can't use L'Hopital's rule to do that if you've already had calculus, because you actually don't know this without that special limit. So there was a rhyme or reason besides just torturing you to do that. Okay. The derivative with respect to x of the natural log function equals 1 over x. The derivative with respect to x of exp of x equals exp of x. And this is an important one. Okay, so this is the log function. Let me actually say what it is so you can look it up. This right here is the exponential function. So exp of x equals e to the x. Yes, those are the same things. But in many places you see this. Especially in biology. So, for example, if I have e to the 5x squared plus 10x to the 5th plus e to the 7/3 x to the 4th and stuff like this, what I'm going to write is exp of 5x squared plus 10x to the 5th plus, and then I'm going to do exp again, exp of 7/3 x to the 4th. It's neater. It's like, a bunch of signs together. Okay? So if I have something that looks like this, I'm going to replace it with something like that. Just because, it's easy to lose stuff in here and I have it communicated. Whereas this communicates. And your book, the book that we're using doesn't do that. But if I don't show it to you, you're going to see it in bio or chem or one of these physical chemistry things, yeah, it makes nested exponents so much neater. So that's why I'm showing it to you. It's not because I hate you. It's because I actually want you to take something from this class besides a decent grade. I want you to have that too. All right. Are there any questions about these? I put a bunch of them up here, right? I got sine, cosine. I got c to the x. I got a constant. I got x to the c. All right. I think that's all the ones you need. I'm going to show you one more. And that's this one. There's one more that's not in the book, or at least not yet. And by not yet, I mean we haven't gotten that far yet. Let f be a continuous function. Let f be defined on an interval d. Okay. If f is continuous, then d over dx, and this function is interesting here. This function is very important a lot of places. AUC FA and A be a number in D. AUC FA of x, the derivative of this function equals f of x. Okay? Keep that in the back of your head. We're going to have that later. What is that? He's doing demon things that aren't in the book. This is why we were number 2 on the test grades, right? If Scott would just stick to the stuff that's on the test, we'd do what? Yeah, maybe I'm doing something for a reason. Just maybe. It's this weird exponent stuff. EXP. Well. Okay, so let's do some examples. Let's mix and match. Right, so here's an example. Let's do d over dx of sine of x plus x to the 5th plus 6. All right, let's do a little mix and match. This is going to equal the derivative of sine is cosine plus 5x to the 4th. Again, positive exponent. I'm just going to plug it in plus 0. Oh, you skipped the sum rule. Don't forget the 0. It's important. That's right. I didn't do the sum rule. I did the sum rule, but I didn't actually write it out because, I had this. Okay. Now, 2. D over dx of 2 to the x plus x to the 5th. This is a lovely function. We are going to have 2 to the x ln of x plus 5x to the 4th. Power rule here. Sorry, not power rule. Exponent rule here. Exponent moved. Power rule here. Base only moved. And I should say exponent only moved here because I can't do this if the exponent and the base are both moving. How do we feel about that one, 1 to 5? Okay. Is that c to the x? You asked this a while ago. Is that c to the x log c? No, it's c to the x natural log c. Okay. All right, let's do another one. D over dx of the cube root of x plus 10 times ln of x. So I'm going to mix and match here. I'm going to do this is equal. Now note here what I'm going to do. I'm actually going to do the sum rule explicitly. So I've got x to the 1/3. I've done nothing here, plus 10 times the derivative of the natural log of x. Now the reason I'm doing that is because I'm actually going to algebraically manipulate one of the terms. So I just kind of did a little thing. Now I evaluate using the power rule. And that's 1/3 x to the -2/3 plus 10 over x. Okay. Shouldn't number 2 be... Yes, you are right. I messed up on number 2. You got me. It should indeed. 2 to the x ln of 2. Now, there's a good question. What is d over dx of 2 to the x ln of 2? Yes, I messed that up. Bad me. Thank you. I did do ln of c up here, right? When I stated the rule? Yes, I did. Okay. Well, do I need another rule for this? This right here, ln of 2, is a constant. Okay? So this is the same as ln of 2 times d over dx 2 to the x. Because that's a constant. And that's ln of 2 times ln of 2 times 2 to the x. All right, 1 to 5, how do we feel about that last one? The fact that this right here is just a constant, ln of 2 is not a function to be evaluated. It's just a constant. It's constant as a number. I just pull it off using the constant multiple rule. Okay. Let's revisit one, and then we'll end for the evening. Okay. So let f and g both be differentiable at x. Then f times g is differentiable at x, and d over dx of f times g of x equals the derivative of the first, f prime of x times g of x plus f of x times g prime of x. Let's do an example. Let's take the derivative d over dx of x squared times times 2x. Now, the obvious answer is multiply this out, right? So with the product rule, let's do something more complicated. Let's do x squared times 2x plus 5. Now, the appropriate way to do this is the power rule, but I want to show you something, and that's why I'm going to do it the more complicated way. Okay? So with power rule, d over dx of x squared times 2x plus 5 should equal the derivative d over dx of 2x cubed plus 5x squared. And yeah, my head's in the way. Equals, okay, now I'm just going to evaluate the derivative. That's going to be 6x squared plus 10x. Now, let's look at this new rule that we have here. And the reason I want it is because I don't always want polynomials. So I can do things with like sine and stuff. I'm going to call this particular thing f. I'm going to call this particular thing g. So what I'm going to do is I'm going to do equals with the product rule. Okay, f prime of x. So d over dx of x squared times g of x plus x squared times d over dx of 2x plus 5. Okay. So what I did was I applied the rule. F prime of x times this, right? This is the same thing as saying this. D over dx of f of x times g of x plus f of x times d over dx of g of x. Same thing. Equals. Well, the derivative of x is x squared, and I need to carry my baggage, plus x squared times the derivative of this is 2, plus 0. All right. Well, that's going to equal x squared times 2x plus 5 plus 2x squared, which is going to equal I'm an idiot. This should be x to the first. Okay, there we go. The derivative of x squared is 2x. Duh. Okay. It's late. And that is going to equal 4x squared plus 10x plus 2x squared, which equals 6x squared plus 10x. It's too late for me. So 1 to 5, how do we feel about that, besides the fact that I messed up that? Oh, Scott messed up an x squared. Let's make fun of him. All right. Now, in Leibniz notation, I could also say it like this. Okay? Let U and V move with X. then dy over, then du times v over dx equals du over dx times v plus u times dv over dx. That's another way to say it. And we'll pick that up then. We'll pick it up there. Pick it up there next week. Next Thursday. I'm sorry, on Thursday. So, tonight, besides me making a bunch of little algebra mistakes, which I do when I'm trying to, do 8 things at once, like watch the chat, and play on the thing and talk about it at the same time instead of just do it. Tonight, we talked about the exponential notation, rules of exponents. We talked about using the power rule and derivatives from some other functions. And then we stated the product rule in 2 different ways, and we even did an example. Next time, what we're going to do is a proof for the rabbit. So we're going to prove the product rule. Prove the product rule. Which is our first proof with the rabbit. And yes, that does show up on the test sometimes, that proof. In fact, it's showed up on the test a lot. Are there any other questions besides the fact that, Scott, how can you be teaching math when you can't even do math on the board? Well, you try doing it while talking at the same time. Anything else? Okay, well, that's it for me tonight. Have a good week. And, the quiz is already posted. Some people have asked in the survey. I have read through the surveys that I post quizzes earlier. I'm going to try to do them on the weekend, the Sunday before, the Saturday before. I don't know if I'll be able to sustain that, but I am going to try. If there aren't any other questions, then good night, and see you next time.